is, always.
No.
No? Really?
Yeah. Which is boring.
Oh. It's barely to give you more work.
No.
Well, good. I'm glad. Are there questions about anything before we keep going on with matrix arithmetic and start into some proofs with it?
Yes.
Yes. You have questions?
Oh.
Oh.
I said you're right.
Oh, I know. I said, are there questions?
No.
No, Alex is right though. Good. All right. Well, let's continue our conversation. So, we all good with being able to multiply two matrices together? Then we're happy with that. All right. So let's talk. There was one more unary operation we need to talk about that I didn't mention, and that is the transpose of a matrix. And then we're going to start talking about some rules of arithmetic. A little bit of that with the using elements of the entries of the matrix to prove some rules of arithmetic. Talk a little bit about inverses of matrices as well, and some other things. All right. So transpose basically is just a reflection. So just to do this by example to start with, let's say we had A is 2175, -1081. If I want to do the transpose of A, then I want to take, well, the notation, at least our notation for our purposes, is going to be an A with a superscripted capital T. Some books use a superscripted little t, but our book uses a capital T. So when we do this, basically what the transpose does is it is a reflection. If you think about it from a visual way, it's a reflection about the line that would go start in the upper left-hand corner and go straight down, or not straight down, but down diagonally. The reflection around that line. In particular, rows become columns and columns become rows. Not unlike when you do inverses of functions, x's become y's and y's become x's. Same kind of idea here. We're going to have rows and columns get flipped. So instead of 2175 being the first row, 2175 will be the first column. Instead of -1081 being the second row, -1081 will be the second column. That's it. Okay. That's how you do the transpose of a matrix. Now, there'll be reasons why we need the transpose for other things that we do, but for right now, we're just interested in playing around with the operation. Yeah, Alex.
So with the original matrix we have like an x1, x2, x3.
Mm-hmm.
This one's all just the same x1, or do we keep?
So, tell me how to write it. Tell me what we need to write again.
So like when we write the augmented matrix, we're like 2, 1, and 7 correspond to x1, x2, and x3.
Oh, okay, I see what you're saying.
Yeah.
Right, so we wouldn't, so in that case, it would be the rows that would correspond to your x1, x2, x3 versus the columns if you were going to do the transpose in that case. Okay. We don't have any call to do that for augmented matrices. Again, the whole reason why we use the augmented matrices is to keep track of the coefficients when we're doing trying to do elimination of variables. If you transpose it and then try to do row operations, it's not going to help you to solve that particular system. So now you could, there are equivalent column operations like there are row operations. So you could transpose and then do column operations, but that seems unnecessary. Yeah, Jack.
So do we transpose so we have the proper M and N's for the matrix multiplication?
Mm-hmm.
Okay.
Well, yeah, we'll talk about how the transpose behaves with multiplication as well. We're going to talk about how There is a, I'll say, a distribution property with respect to the product. You just have to do something extra along with it. So we'll actually talk about that when we get to it.
All right.
Yep, yep. All right, so in general, so to write this down, in general, if A, and I'll specify the entry. So if A, capital A has little a sub ij as its entries, and it's an M by N matrix, then A transpose, I'll write it as, I'll say B sub ij, is an N by M matrix, because again, columns and rows get flipped around, right? So if A is M by N, A transpose is N by M, and I needed to identify how I get the entries algebraically or symbolically, whichever way you want to think about it. To get the entry for the transpose, we simply flip the subscripts for the entries in A. So the arbitrary general entry in A transpose looks like a general entry from A, except that if I'm in row I and column J for the transpose, I pick out the entry that's in row J and column I for the original. Because again, we're doing that reversing of roles, right? We're changing the roles of the row and the column in this case. Not unlike what you do when you do inverses of functions, right? If you think about graphically, when you graph an inverse, if you take the point xy, you flip it and graph the point yx to get the inverse. Same concept, same kind of concept, right? I mean, this isn't a function, so right, it's got this rectangular array of things. It's the same kind of concept in reversing the roles of x and y, or rows and columns in this case. All right. Before we get to rules of arithmetic things, let's just see how we can rewrite some things, and I'll play with the transpose too. So we did talk about representing a system of equations using the augmented matrix. We can also represent a system of equations using a matrix equation and utilizing matrix multiplication. So let's look at just an example here, just with numeric example. Let's say we had 3x1, 7x2, plus x3 equals 5, negative 2x1 minus 6x2 plus 5x3 equals negative 2. I'm just making up numbers. x1 plus 2x2 minus x3 equals 6, say. I'm not interested in what the system is or what a solution in that particular system is. I don't really care, or even if it has a solution. All I want to do is try to rewrite this as a matrix equation utilizing matrix multiplication. And the reason why I think about utilizing matrix multiplication is notice that this x1, this x2, this x3 is in each of these entries, right? Where the coefficients have changed, there's a 3, a 7, and a 1. And it looks like we're doing that, like we mentioned last time, if you're familiar with it. It looks like that dot product idea, right? It looks like I'm taking a 3, 7, 1, and taking those entries in a vector and multiplying it by x1, x2, x3. And then the same thing happens in the second row. And the same thing happens in the third row, right? But x1, x2, x3 stays the same, and we're taking the 3, 7, 1 and matching it up with the x1, x2, x3. We're taking the negative 2, 6, 5 and matching it up with the x1, x2, x3. And the last one as well, right? So we notice that, at least I hope we notice, that I can take, if I think about matching it up with the x1, x2, x3, that would be the column I would need to match it up with, right? It's the one that stays the same as I go down the rows, correct? Okay. Out in front, to get this first, I'll say first left-hand side, because it's not the whole equation. To get that first one, I need to match up the 3, the 7, the 1 with the x1, x2, x3, right? If I multiply these two things together, I would match the 3 with the x1, the 7 with the x2, the 1 with the x3, and add them. Right? What would we have for the second row?
-2, -6, 5.
Good. -2, -6, 5. And notice again, if we do the matrix multiplication, it matches up exactly, correct? Like we want it? What would the last row be?
2, -1.
Good. All right, so what we've done here is taking the coefficients and made this matrix on the left-hand side, and made our variables that we're trying to solve into a, well, refer to as a column matrix or a column vector. Either word is fine. Like I said, we're going to talk more about vectors later on this semester. So I'll use the word. If you're familiar with vectors, right now they behave just like you had used vectors in the past in physics class or Calc 3. They behave exactly the same way. We're going to abstract the notion of vector later. Yes, Jack, sorry.
So all of the x1s are in the same column, but the x1 is in the first row. Why is that?
Because remember when we define our matrix multiplication, basically we do a transpose, right? I match up the row with the column, and I do the row with the column. So when I take this and flip it and basically transpose it, it matches up with that row.
Okay.
That's just with the way we define the matrix multiplication. That's why it ends up that way. All right, so I want to change this into a matrix equation. So what do you think the right-hand side should be equal to? Let's think about what would happen if you actually do the multiplication now. If I take this and match it with this, we get what I circled, right? So that would be your entry up in the 1, 1 spot if I actually did the multiplication, right? So what should that be equal to, do you think, as far as a matrix goes?
3x1, 7x2.
I agree. That's what the entry would be. When I want to set up an equation from the original system, what should that be equal to when I'm done? 5, right? I should get a 5 up here, correct? Or whatever that scribble is. I should get a 5 up here, right? Because again, we're trying to represent the system using a matrix equation. You're right. You're exactly right. If I actually carry out the multiplication, that 1, 1 entry would be 3x1 plus 7x2 plus x3, right? We would want to set that equal to 5 when we're solving it. So what should the second one be?
-2.
And the last one should be 6, right? So this is our associated matrix equation, a matrix equation that's associated with the system of linear equations. So every system of linear equations that you can write down, there's an associated matrix equation that you can also write every single time. Okay? So in general, if you've got A11x1, A12 x2, A1n xn equals B1, and then we have a second equation. This is our, oops, that's not a B. This is our standard way that we wrote just a general system of linear equations before. If we've got this system, generally, then we can pick off the coefficients to make our matrix. So all I'm doing in the matrix part is just taking the coefficients and making the matrix of coefficients, or what we refer to as the coefficient matrix. Then we've got that column vector of variables. And then we'll get a column of constants. All we're doing here is rewriting the system as a matrix equation. Now again, we've had a couple of different ways now that we're writing systems of linear equations. The first one was taking the system and making an augmented matrix. Right? Now again, we don't really apply, we can, but it doesn't really help us for solving purposes to apply rules of arithmetic to an augmented matrix. Because if we're using the augmented matrix to solve the system of equations, we're doing row operations, right? Now we're trying to take that matrix and, well, there are some special matrices that we'll talk about later that we can actually accomplish the row operations with. But for what we do right now, we're not really doing matrix arithmetic, right? You're taking a multiple of one row and adding it to a second row, or swapping a couple of rows, or multiplying a row by a constant, right? Not really doing matrix arithmetic. Now, it turns out that you really are, and we're going to talk about why, but for our purposes right now, it doesn't look like matrix arithmetic, right? But this one looks like we could start doing some matrix arithmetic things on it, right? In particular, use the multiplication things. Okay? For example, if these weren't matrices and we just had two constants and a variable, so like 3x equals 9, what would you do to solve for x? Divide by 3, right? So if I wanted to try to get this vector by itself, you might think, is there a concept where I could divide by a matrix? Well, yeah, there is a concept where we can divide, and we don't call it division, and we don't write it as division, but there is a concept of being able to divide or move the matrix to the other side, which we're going to talk about here in a little bit. Okay? So this is just another way to express the system and also give us another way to be able to solve the system, if you will. All right. So again, this is our matrix equation that's associated with the system of linear equations. And we're going to come back to this concept, well, several times. All right. So one more thing we notice is that if I do this matrix multiplication, I'm just going to use this as an example. If I had a second column here, I don't, but if I had a second column here, the entries in my answer for my second column don't depend on the first column at all, do they? No. Okay. So let me write this down just real quick as far as the notation. I'm going to give you a slightly different notation and then go back to that idea. A lot of times we'll use a capital A here. Of course, we use capital letters to denote the matrix. The other two are matrices, but they're really vector ideas. It's really a single column. Your book will put it in boldface for that particular notation rather than using a capital letter. Of course, it's really, really hard to write in boldface on the border on the surface here. So what I write and what you'll see when you're writing is that you'll put a little arrow over the top. And I'm lazy, so I don't ever put the other side of the arrowhead on there because I can do that in one motion. And then I don't have to backtrack to get the bottom of it. So this is the same thing as in your book. It would have an X that's bolded, and I have to color it in like that. Okay, which I'm not going to do every time I try to write it. So you would have the same thing over here on the right-hand side. I'd have this constant vector on the right-hand side. Again, the idea behind this is these are still matrices. We're just writing it in a slightly different form because they only have one column. All right. So back to the idea I was just mentioning a minute ago. Let's say we do this for a very small example. We do this with letters. This is a very, very small example. But the idea here is something that we're going to come back to later. We already know how to write down, we already know how to write down the answer to this multiplication, right? Because we match up rows with columns. Okay? But what we notice here again is to get the first column in our answer, we will go, for example, to get the 1, 1 entry, we would take the first row times the first column, right? And to get the 2, 1 entry, we'll take the second row times the first column. That second column doesn't have anything to do with it, right? Okay? So one of the ways we can write this is if I call this matrix A, and I have a column vector that forms the first column, and a column vector that forms the second column, and I'm only putting those little vertical lines on it to denote that it's stretching out over the entire column. Okay? That's just my notation to tell you that I'm talking about a whole column of entries. When we do the product, notice to get the first answer, the first column of the answer in the product, I only take this matrix and multiply by the first column, right? That's all we, right? When I get the first column of the answer, you'll match this row to that column, right? And then you'll match this row to that column, right? Okay? So, when we get the answer, I can think of this now as a couple of new column vectors. I can take the A and multiply by the B1. That gives me a column vector, doesn't it? And I can take the A and multiply by the B2, and that also gives me a column vector. So I can think of this, and this works out generally too. Okay? It doesn't have to stop at 2 columns, right? But I can think of this matrix multiplication in this fashion. That I can take the whole matrix multiplied by the first column. I can take the whole matrix multiplied by the second column, and so on down the line. Now, you may not see why I care about this right now, but we will come back to this idea. Well, I'm mentioning it now since we. You see does it make sense what I'm saying though? To get this first column, I've got to take the whole matrix and multiply by the first column, right? Because up here, to get the upper left-hand corner, I take row 1, column 1. To get the lower left-hand corner, I would take row 1 and column 1, or row 2 and column 1. So again, yeah, Megan.
Can you write it out?
Write out.
The actual multiplication.
Okay. Well, it's going to look really, really weird, but I can do that. I'm not sure it's going to help. Okay. So your actual multiplication, if I just wrote out the entry, we agree it would be. Let's see. Lost my train of thought. This would be your first column, right? We agree with matching up the first row, first column, second row, first column?
Yeah.
Okay. I'm not, I could write the second column in there, but I don't really care. Because, all right, this is going to look weird. That's the same thing as that in the first column. That's what I'm saying. Because if I ignore the second column, that's the product we do. And if I ignore the first column, then I would just replace the BC with the D and E. Did that help?
A little bit.
A little
So
bit.
you're multiplying like your A11 by your B,
Mm-hmm.
and your A12 by C.
Right.
So like,
Yep. Because we're going to match that row up with that column, right? When we fill out, basically all I really care about right now is that when I fill out the first column, I don't care about the other ones. I only care about the matrix that's out in front and the first column. That's all this is saying. When I fill out the second column, all I care about is the matrix that's out in front and the second column, and so on down the line. That help a little bit? Okay. All right. So, like I said, I'm not going to make you do this right now. I just want to introduce it now. We're going to come back to it later. It's going to be a little while, but we're going to come back to it later. Okay. You could think of it the same way as rows, by the way. If I wanted to be creative, and this is something we'll talk about later, and I'm not going to do it right now and write it down. But I can think about each of these as being what's referred to as a row vector, and having the whole matrix on the right, and then getting your rows in the same fashion. All right. Anyway, let's talk about then a little bit about rules of arithmetic. So taking back again to the idea of trying to solve that equation. Remember again, algebra has its roots in solving equations. I know some of you are in history of math. You got lots of roots of lots of different things, right? But you're going to see about the history of solving equations. Right? It's where algebra has its roots. Okay? This is also a good joke, right? Because there's roots, algebra. Ha ha. Okay. All right. So anyway. All right. So to get to some rules of arithmetic, we've already defined addition. We've already defined multiplication. We've defined the transpose. There are 13 properties that are listed on page 39. I'm not going to write them all down, but there's 13 different properties of arithmetic on page 39. Those properties are properties that you would expect to happen with matrix arithmetic. For example, the first property is that addition works both directions. That A plus B is B plus A. Okay? Yeah, again, if you go to page 39, there's a blue box, you'll see it. So the whole thing of that particular box is just to tell you that a lot of the properties that you've dealt with real numbers hold over for matrix arithmetic. Okay? So when I gave you when I did that on the video, I showed you that matrix multiplication distributed over sums. So let's do one like that. See if we can do another one like that. Let's see. Let's do the other side. So let's say we had, this is actually property E in theorem 1.4.1 on page 39. So it says that B plus C times A has to be BA plus CA. All right, so one of the reasons why I want to talk about this particular property is because notice that the one I did in the video, and I know it's been probably a couple of days since you watched the video, but the one I did in the video had the A on the left-hand side, right? Why do we need two different properties when we're talking about distribution? Because you're used to saying, well, A times B is the same thing as B times A, right? So if I have A times B plus C gives me AB plus AC, it should work on the right-hand side too, right? Well, the issue is that with matrix multiplication, we don't get the same answer both ways necessarily, okay? As a matter of fact, if you just take two random matrices and multiply them, say I take 1, 2, 3, 4 and multiply it by 1, 3, 7, 2, making it up, you get 1 times 1 plus 2 times 7, so you get 15 in the upper left corner. 1 times 3 is 3, plus 4 gives me 7. 31, and 9 and 8 is 17. If I did my arithmetic right. I know I did it quickly. All right, but just matching up row to column, row to column. Okay. All right, but if I go the other way, we did mention the other day that, sometimes the matrix multiplication is defined one way but not the other. right? We mentioned that the other day, because you have to have the right number of rows and columns to be able to get things to match up. But even if we can multiply both ways, we don't necessarily get the same answer. 14 and 8 is 22. Right? When I take the row 1, 3 and match it up with the column 1, 3, I get 10 up in the upper left-hand corner, right? Which is already different from the 15 we got before. Yeah? So I get this, I get different answers. So matrix multiplication is not commutative. Okay. So just write that down. Matrix multiplication is not commutative. So this is why I need to have a second property. For real numbers, we know that multiplication works both directions, right? So if I have distribution from the left, I should also have distribution from the right. It's just rewriting the product in the other order. But for matrix multiplication, that doesn't work. Okay? We don't necessarily get the same answer. Now you can. There are examples of matrices that will commute when you multiply them, but in general, it does not. Okay. If you've had Calc 3, you've seen an example of a non-commutative product before. If you've done the cross product, right? Cross product of two matrices isn't necessary. Well, I'm sorry. Cross product of two vectors is not commutative. In particular, when you flip them around, you get the negative, right? Okay. This is even worse. I don't even have the same values that come out, right? None of those values even match. So it's even more, in some sense, it's even more non-commutative than cross product, right? If there are gradations of being non-commutative, this one's even more non-commutative than cross product. Because cross product, you get the same numbers. They're just the negatives of each other, right? And if you think about vectors and right-hand rule idea, right, it's either up or it points down, depending on which one you did first. And if you haven't had Calc 3 and know what I'm talking about with right-hand rule, you have no idea why I'm doing this. But, right? But that's the idea, right? Literally the numbers are the same. It just points in a different direction. And usually when you use the cross product, you're not worried about which direction it's pointing in. Right? Because things that you use the cross product for are to find a normal vector to a plane. Well, if it's perpendicular to the plane pointing up, it's perpendicular to the plane pointing down, for example, right? If you're looking for the area of a parallelogram defined by two vectors, you do the absolute value of the magnitude of the cross product, not the absolute value, or the norm of the cross product, right? Well, norm doesn't matter if it points up or points down either. Magnitude doesn't matter if it points up or points down. So usually when you're using the cross product for things, you don't really care which way it pointed, because you're going to do something else with it anyway, and the pointing direction didn't matter. Right? If you've had Calc 3. If you haven't had Calc 3, then don't worry about what I'm saying. Okay? Ignore all of it. But I'm trying to relate it to other things. All right. Anyway, this is even worse from that perspective, right? The numbers actually come out to be completely different in this case, depending on which way you multiply. This is why we need a second property of arithmetic that talks about multiplying from the right as well as multiplying from the left. Okay. Now, the approach will be the same, how we need to prove this, but we still need it, which is why there's 13 of these things listed in there. Because we have to make sure if there's anything with multiplication, we have to make sure it works from both sides. So in particular, there's 4 of them just devoted to multiplication, distribution of multiplication, because we need over sum, over difference, and then on the right too. Okay, so that's why there's 4 of the 13 are just devoted to being able to distribute. All right, so let's see how this works. All right, so we're going to let A have some general entry. Oops, I'm going to leave a little spot here for the subscript. B be a general entry, and C be some general entry. Oh my goodness gracious, why can I not write the I first? All right, so let's talk about subscripts. Let's go back, let me scroll back up a little bit. Nope, it's too far up. Let me just rewrite it. That's what we're trying to prove. Yours is probably still on your paper where you can see it. Mine was off the screen. All right. What do we need to do to make sure that we can even define this? So first, let's just look at, I'll worry about the right-hand side in a second, but let's look at the left-hand side. In order to be able to do B plus C, what has to be true about B and C? They have to be the same size, right? So if I want to write down subscripts for B and C, I can do M by N maybe for both of them. Whatever. I just want to make sure they have the same dimension and not necessarily have the same rows and columns. Right? Doesn't have to be a square matrix. Nothing said that it had to be square. All we know for certain is that to be able to add them, I have to make sure I have to have the same dimension. All right. After we add them, what will the dimension will be the same, right? It'll still be M by N. What has to be true then about the size of B plus C and the size of A in order to be able to multiply it? What has to be true? Okay.
A has to be N by P.
Okay. Yeah, so I know that the number of columns here in B plus C has to match the number of rows here, right? The dimension of rows to columns. Okay. So like Jack said, I need to have n rows, but the columns can be whatever. Right? So I'll use a P. That makes sense to everybody? Why I've got those different subscripts there? You okay with those? Yeah, Megan.
So it's because if you're doing, because you have to multiply like the N in the B by the A, that has to be the same number so that you can multiply them.
Mm-hmm. That's right, yep. So when we're done with this multiplication on the left-hand side, what size matrix should we end up with? An M by P, right? Because this has M rows and this has P columns. That's the pieces, those are the dimensions that survive. Okay, now let's look at the right-hand side. Make sure we get the same dimension when we're done. That should be check 1, right? In order for these matrices to be equal, they have to have the same size. Right? Okay? So let's look at the right-hand side. B is M by N, A is N by P. So the result will be M by P, and this one will also be M by P. If we add them, they'll still be M by P, right? So just to write that down. Oops. Right? In order for two matrices to be equal, they have to have the same size to start with, right? We need more things too, but we need to make sure they have the same size. So that was the first check that I did, was make sure that the left-hand side and the right-hand side were going to be the same dimension when we're done. Does that make sense? Okay. All right, so then again, just like what we mentioned on the video, and if you've seen set proofs, it was similar to the set types of proofs you do when you're doing subset ideas. I want to see what a general entry looks like over here. I want to see what a general entry looks like over here, and show that they have to be the same. Okay? All right, so let's start with inside the parentheses. You already told me, oops, not B. You already told me that when I add B plus C, we get an M by N matrix. how do you get the general entry for the sum of the two matrices? What do we do with the original entries to get the sum? Add them together, right? So our D sub ij will just be B sub ij plus C, oh my heavens, C sub ij. Right? We agree? Yeah? Okay. So if I go to the next one, when we take B plus C times A, and I know I'm skipping the letter E, we usually use the letter E for a different purpose, which is why I'm skipping it. And it's not because it's the, number 2.718 and change. We'll talk about why I'm skipping the E in a little while. All right. What size did we say this has? M by P. Good. All right. So now I need to talk about what the general sum or the general entry looks like. Okay. So let's think about how we get this. All right, so if I think about say I have row I, I'm just going to write this over on the board, for some matrix where I have, what letters am I using now? I got D, I1, DI2, DIN, and then I have column J, and I'll have an A1J, A2J, AM, NJ. Right? To get the IJ entry, we match row I to column J, right? That's how we get the IJ entry. We match row I to column J. Notice what changes. This I does not change, right? This J does not change. It's the pieces in the middle, right? Right? And we're going to be changing this subscript as we go along. The second subscript changes here. The first subscript changes here. And we do that product and add together, that dot product idea, right? So this F sub ij will be a summation. I'll use the letter K here. K equals 1 to N. It's D sub I K, A sub K, J. Again, look where these come from. Why do I have a K in the the second subscript for D and the first subscript for A? Well, what was changing? If I will go across the row, what changes? The column changes, right? So we go across a row, the column changes. We have to match that up with what's going down the column. If we go down the column, the row changes. That's why this index of the sum is where it is. Right? This is representing going across the row. This is representing going down the column and then matching them. Does that make sense? Okay. All right. Now we also know that we know what D sub ik is equal to because we know what D sub ij is equal to. What can I replace the D sub ik with?
B sub I K plus D sub I K.
Good. And the reason why we're using K's here is because I have a K here, correct? Rather than using a J, right? I have a K here, so I use a K here. Now, good news is that now that we're at this point, we're in the good old land of real numbers. Right? All these entries are real numbers, so I get to use your real number properties. What can I do with the A sub kj? Yeah, I can distribute it. And now I've got a sum of a sum. So I can split the summation up over both pieces. Now it's probably about as far as I can go with simplifying things, but I'll go ahead and do that. Now, again, think about why I broke this up. When you're doing proofs, we're doing a proof here, by the way. When we're doing proofs, don't lose sight of where you're trying to get to. What are we trying to prove? Generally, what are we trying to prove in words? We're trying to prove a distributive property, right? So I broke this down as far as I can get to look like a distributive property, right? I've got a B times an A and a C times an A. So I just worked with this until I got to that point. Okay. Now, you might recognize this now as what you want, but a general way for doing these types of proofs is to work with one side, see what the general entry has to look like, work with the other side, see what the general entry has to look like, and show that they're the same. Okay? So let's go over to the other side. If I do B times A, I need another letter. I'll call it G. What size does B times A have? M by P. And now I have to figure out what this general entry looks like. Well, it's a general entry of a product. For a general entry of a product, we got to go across columns and down rows, right? So we get a summation idea. So this will be the sum k equals 1 to n, b sub I k, a sub k j, right? Because again, we're going across the columns of B and down the rows of J, or A, main letters. Right? And then similarly, what do we have for CA? What's going to be the difference between CA and BA?
There's going to be a C where the B is.
Yeah, good. Ooh, I've run out of letters. Whew. I better use like an R. All right, so if I now add BA and CA together, what size does BA plus CA have? M by P. And what does that general entry have to look like? How do we get R sub ij? What do we add together? But, yeah, I'm going to write it in 2 steps. But yeah, it's these 2 entries added together, right? It's your G and your H. And then I'll substitute notice I'm trying to do this in steps so you can see where the substitutions are, hopefully. But what else had this same form? I forgot what the letter was I used. What else has the same form? I think it's F, isn't it? F sub ij? Okay. So did we just show that the general entries are the same for the 2 matrices?
Yeah.
Yes. Did we say that they had the same size? That the 2 matrices had the same size? Yeah. Yes. So thus, we know that B plus C times A is equal to BA plus CA. Shoo!
do anything like this on a test, are we?
Oh, yeah.
Like this exact one?
It'd be likely, but yeah, you'll have to do a proof for that one. That's like the entries of matrices.
Oh, fun. Will it be this long?
No.
Okay.
But yeah, she'll have to do it.
I like that.
It's not bad. It's okay.
It's just a lot of.
I could have skipped some. I could have combined some things together, but I was trying to write it out very explicitly so you could see what was going on. In particular, especially with some of the proofs that you have to do with these, you can get lost pretty quick in the notation. For example, one of the things that we do, one of the things that we'll talk about is how the